We're going to go ahead and look at trying to find the volume of objects that are revolved around either horizontal or vertical axes. Now up to this point we've been able to go ahead and find the area underneath of a curve by using integrals. Basically we were looking at, hey, we can divide this into lots of little rectangles with a width of w and a height of h. And then all we have to do is go ahead and add all those little rectangles together. Well, as we start to look at the Riemann sums, our width became our delta x, how wide each rectangle was, and our height really was our function. And that's what we have here. And if you do the limit of this here, you really end up with your definite integral, where the width of your rectangle is your dx and your height is your function. And so the area underneath our curve up here using rectangles can be approximated by this definite integral, where the height is our f of x and the width is our dx. And we're going from a to b. We can actually go ahead and extend that a little bit so that we can help us do volumes of revolution. When we look at all these objects here, the line going through the middle of them is your axis of revolution, and then you're just taking one small flat two-dimensional shape and rotating it about that axis of revolution, and then you end up with this three-dimensional shape. Going ahead and doing that is helpful for finding volumes of all these practical things that you see here. Well, if we take our rectangle that we know how to find the area of underneath the curve and just revolve that around your axes, we end up with a disk like this. Well, the volume of a disk is really just the area of your circle, which is pi r squared, times the width, how wide or thick your disk is. So we can really take and extend what we were doing before with our rectangles for area underneath the curve, really take all those rectangles, revolve them around our axis of revolution, and we get lots of little disks. So really, for the most part, all we have to do to find the volume of volume of something revolved around a axis of revolution is to really add up all those disks. To add up all those disks, we knew that it was this for our rectangles, height times width. So we're going to do that same type of thing down here, but we're dealing with our area of our circle times our width for the volume of a disk. And then we're going to do all those. So it's your radius squared, which is your function, times your dx, all times pi. The dx, the delta x is your dx. The radius is related to our function going from our axis of revolution out to the edge of our function that we're revolving. And then we have our pi in front. If you have a horizontal axis of revolution, you're dealing with x's. If you have a vertical axis of revolution, you're going to be dealing with y's. So let's go ahead and take the region that's shaded by this graph, the square root of x, and our x equals 4. So we have our x equals 4 with our shaded region here. We're going to revolve that around the x-axis. So when we revolve that around the x-axis, it's going to form a shape that looks like this here, where this wooden dowel going through the middle of it is our x-axis. And you can see all the different disks that would be formed. All we're going to do is use our integral to be able to approximate, or not approximate, find our volume. We have our pi. We need to have our lower bound and our upper bound. Since it's a horizontal axis of revolution, we need to be dealing with x. Your bounds then are the left and right edges of where you're shading. You're starting at 0, going over to 4, so our bounds go from 0 to 4. Our radius is going to be going from our function to our axis of revolution. Our function is the root x down to our axis of revolution, which is 0. So our radius is going to be root x minus 0. So we just get root x because subtracting 0 doesn't make a difference. And now remember, we're looking at volume of a disk. That's the area of a circle, which is pi r squared. So we got to take our radius and square that. So that simplifies down just a little bit. And then we can just do our basic integration to be able to go ahead and find our volume. Plug in our 4 minus what we get when we plug in 0, which doesn't change it, and we end up with 8 pi units cubed.